We are presenting orthogonal over-parameterized training. The empirical generalization of neural networks is typically determined by how the network is structured and how the network is actually trained. Our work focuses on a brand new training framework that is independent of these two aspects. Our first motivation comes from over-parameterization of linear neural networks. For example, performing gradient descent on factorized matrices may yield better generalization than performing gradient descent on a single matrix, as the example in the slideshow. Another evidence of why linear over-parameterization is useful comes from one of our previous work. Here we show that learning a linearly over-parameterized neuron yields consistently better generalization on visual recognition. The second motivation comes from the empirical observation that encouraging hyperspherical diversity leads to better generalization. Specifically, we characterize the hyperspherical diversity as the hyperspherical energy of the neurons, which is defined by the sum of pairwise neuron similarity on the unit hypersphere. Our goal is to propose a principal training framework for neural networks that consists of the following advantages. First, we want to make use of the over-parameterization from linear matrix computation. Second, we want to naturally guarantee the minimum hyperspherical energy. Third, we want our framework to be compatible with different network architectures and different optimizers. To this end, we propose orthogonal over-parameterized training. The basic algorithm works as follows. We first randomly initialize the neurons with zero-mean Gaussian distribution, and then we learn a set of layer-shared orthogonal matrices that transform these neurons. The reason that we want to constrain the transformation matrix to be orthogonal comes from the empirical training dynamics of hyperspherical energy. We observe that even the baseline CNN starts with a very small hyperspherical energy. Inspired by this, we further prove that once we initialize the neurons with zero-mean Gaussian distribution, the hyperspherical energy will be perfectly minimized. Therefore, we only need to learn orthogonal matrices that do not change the hyperspherical energy. We propose 4 ways to guarantee orthogonality of a learnable matrix, including unrolling orthogonalization algorithms, orthogonal parameterization, orthogonality preserving gradient descent, and orthogonal regularizations. We show that our training framework yields a more convex and more smooth loss landscape. Moreover, we give provable generalization guarantees for our method. We conduct a few ablation studies to justify our design choices. Moreover, OPT works universally well on different network architectures and different tasks. One shortcoming is that our original framework may need to learn large orthogonal matrices in some certain cases, which is computationally prohibitive. To address this, we propose stochastic OPT, which approximate large orthogonal matrix with many much smaller ones. Specifically, we randomly select a subset of the neural dimensions in each iteration, and then perform OPT on this subset. We also show that stochastic OPT yields comparable performance to OPT, but is far more scalable and parameter efficient. Finally, we demonstrate another useful application of OPT, which is to simply apply OPT to the classifier layer. Taking advantages of OPT's parameter efficiency, we can make the number of parameters in the classifier layer to be independent of the number of classes. Therefore, for a large number of classes, OPT works much more scalable than the standard training. Thank you.